So our fourth example is the all pairs shortest path problem. That is to find the shortest path between all pairs of vertices. In the fundamental course, we have studied Dijkstra's algorithm, right, for finding the shortest path from a single source. And certainly we can apply Dijkstra to every vertex as a source for v times, right? That is okay if the graph is sparse. But if the graph is not so sparse, for example, a complete graph with edges between every pair of vertices, we have a better one. And this algorithm is called the Floyd algorithm and is a DP algorithm. We discussed this one because the way it defines a subproblem is a little bit different and therefore interesting. First of all, we must store the path length in a two-dimensional array, right? So call it Dij for the shortest path length between vertices I and j. In the previous two problems, in order to find the solution for the whole data set, we define a subproblem that contains only part of the data, right? And then to divide and conquer to break it into parts of smaller sizes, right? But not in this case. Let's think what we did with Dijkstra's algorithm. We were collecting the vertices one by one into the final solution set, right? Once a new vertex is counted in, we would update the other vertices that were still outside. So although they are not in yet, their conditions are getting better and better as we were collecting more and more vertices into consideration, right? Now, let's extend this idea to all the pairs. So this is the most interesting part. Let's define the subproblem to be the problem that involves only part of the vertices. All right. We still maintain the distances between all pairs of vertices, but those distances are not really the shortest ones. They are the shortest distance from I to j, but passing through only the vertices that is smaller than or equal to some k. That means at this stage, we are only taking the first k vertices into consideration. Okay, so we start from the initial cost matrix. Okay, let's denote it to be d sub negative 1. That's the initial condition. And then we begin to update this matrix by incrementing this number one by one. That means we're collecting more vertices one by one into consideration. So for example, when we start from cos of ij, and next time we're supposed to obtain d sub 0, means that we're going to update all the distances to be the shortest distance from I to j passing through only the vertex 0. So step by step, the final length of the real shortest path from I to j is going to be what? It's going to be d sub n minus 1. Well, the vertices are indexed from 0 to n minus 1. So that means we have considered all the vertices, and this is the real shortest path. Okay, so the algorithm is we start from the cost matrix d sub negative 1 and successively generate d sub 0, d sub 1 until we finally obtain d sub n minus 1. Okay, so basically this is the definition of a subproblem. To continue thinking in the dynamic programming way, the next step is try to find the relationship between this subproblem and the subproblem of smaller sizes, right? So the key is here. Suppose that a smaller size problem is already solved. Then when we collect one more vertex in, when we collect k in, what's going to happen? There are going to be two possible situations. One is that this new vertex k doesn't belong to the shortest path from I to j, and therefore nothing will change. So d sub k will be the same as d sub k minus 1. Or if k does belong to the shortest path, meaning that if by taking this k into consideration we can obtain a shorter path, then if k does belong to the shortest path from I to j, then this shortest path must consist of two parts. One is the shortest path from I to k, passing through only the vertices that is strictly less than k, right? And then the other part must be the shortest path from this k to j, passing through only the vertices that is strictly less than k. So these two solutions must have been obtained from the previous step. So here we go. The optimal solution of the current subproblem can be constructed from the optimal solutions of smaller sized subproblems, and those solutions have been obtained before we get to this stage. So sum them up, the way we compute d sub k from d sub k minus 1 is this. Right? So every time we increment the k, let's compare these two numbers and take the smaller number into the next iteration. All right, is that simple? So we have an extremely simple pseudocode for this Floyd algorithm. Okay, so basically step 1, we just initialize this distance array to be the cost matrix, and then jump into this for loop of k. Okay, for each fixed k, we consider for every pair of I and j, compare dij with the sum of dik and dkj, right? And if this number is smaller, we update it to be the smaller number. This is quite straightforward, right? And obviously the time complexity is what? Since there are 3 nested for loops, it's going to be n cubed. Well, actually, if we only look at the big O notation, it's the same as we apply Dijkstra's algorithm for n times. It's also big O of n cubed. But practically speaking, it's faster than Dijkstra with a very dense graph. For example, especially when it's a complete graph, for complete graph, this algorithm is quite tight. So this upper bound is quite tight. Well, say again, if you're asked not to only find the shortest path length, but also try to reconstruct the path, then you have to record the path while we were calculating the path length. And again, I leave it as a homework to go through the pseudocodes by ourselves after the class. One detail is that this algorithm works if there are negative edge costs, it's okay. But if there is a negative cost cycle, it's not going to work.